Imagine a place in space where gravity is so powerful that not even light can escape. A place where time slows to a crawl, and the laws of physics as we know them break down. This is the realm of a black hole, one of the universe's most enigmatic and terrifying phenomena. But what are these cosmic monsters, and how do they defy everything we thought we knew about reality? Black holes begin their lives in chaos. When a massive star, at least 20 times heavier than our Sun, exhausts its nuclear fuel, it no longer has the energy to fight gravity's relentless pull. The star collapses inward in a cataclysmic explosion called a supernova, leaving behind a core so dense that it warps space-time itself. This is the birth of a stellar black hole, a gravitational trap with a radius smaller than a city, but a mass greater than our Sun. Yet, even these are mere specks compared to their cousins, supermassive black holes lurking at the hearts of galaxies, weighing millions or billions of solar masses. How did these giants form? The answer remains one of astrophysics' greatest puzzles. Every black hole has two key features: the singularity, an infinitely dense point at its center where all laws of physics dissolve, and the event horizon, the point of no return surrounding it. Cross this invisible boundary, and escape becomes impossible. Even time, as Einstein revealed, bends to the black hole's will. To an outside observer, a clock falling into a black hole would appear to tick slower and slower until it freezes entirely, a haunting illusion created by extreme gravity. The idea of black holes emerged from Einstein's theory of general relativity in 1915, but even Einstein doubted they could exist. It wasn't until 1964 when astronomers discovered Cygnus X1, a star orbiting an invisible, massive object, that the first black hole was confirmed. Today, we know they're everywhere. Our Milky Way alone may harbor millions of these invisible predators. But the more we learn, the stranger they become. Take the Schwarzschild radius, the mathematical boundary defining a black hole's event horizon. For Earth to become a black hole, it would need to be crushed into the size of a marble. For a star, it's a few kilometers. Yet, despite their crushing density, black holes are not cosmic vacuum cleaners. They don't suck matter indiscriminately. They're more like gravitational anchors. If our Sun magically became a black hole, don't worry, it's far too small. Earth would continue orbiting peacefully, in total darkness. What truly lies inside a black hole? Einstein's equations suggest a singularity, but this is where physics itself collapses. Quantum mechanics and relativity clash violently here, hinting at undiscovered laws of nature. Some theorists propose black holes are gateways to other universes. Others argue they're holograms, storing information on their event horizons like cosmic hard drives. Black holes challenge our understanding of reality, but they also illuminate it. They're the ultimate paradox, both destroyers and creators. When two black holes collide, they shake the fabric of space-time, sending ripples called gravitational waves across the cosmos. These waves, first detected in 2015, have opened a new window into the universe and revealed black holes merging in darkness billions of light years away. Yet, for all their power, black holes are fleeting. Stephen Hawking stunned the world by showing they slowly evaporate, leaking particles in a faint glow now called Hawking radiation. Given enough time, trillions of years, even the mightiest black hole will vanish in a flash of energy. But what happens to everything they've swallowed? Where does it go? The answer may lie in the quantum shadows of the singularity, or somewhere beyond. As we peer into the abyss, one thing is clear. Black holes are not just cosmic oddities. They're keys to unlocking the universe's deepest secrets. And the journey to understanding them has only just begun. Black holes are, by definition, invisible. They don't emit light, and their gravitational pull traps everything, even photons. So, how do we study something that can't be seen? The answer lies in the clues they leave behind, the way they warp space, the light they rip from nearby stars, and the ripples they send across the cosmos. One of the most dramatic ways black holes reveal themselves is through their accretion disks. When a black hole pulls in gas, dust, or even an entire star, this material doesn't fall straight in. Instead, it spirals around the black hole, forming a glowing disk of superheated plasma. Friction and magnetic fields heat the disk to millions of degrees, causing it to emit X-rays and other high-energy radiation. These accretion disks are like cosmic lighthouses, signaling the presence of a black hole even when it's shrouded in darkness. The first black hole ever confirmed, Cygnus X1, was discovered this way. In 1964, astronomers detected intense X-rays coming from a binary system in the constellation Cygnus. They realized the X-rays were coming from an accretion disk around an invisible object, a black hole devouring its companion star. This discovery marked the beginning of a new era in astrophysics. But not all black holes are so obvious. Some, like the supermassive black hole at the center of our galaxy, Sagittarius A, are quieter, feeding less voraciously. To study these, astronomers rely on the motion of nearby stars. By tracking stars orbiting an invisible point at incredible speeds, they can calculate the mass and size of the black hole. In 2020, the Nobel Prize in Physics was awarded for precisely this work, confirming Sagittarius A star as a supermassive black hole. Then there are gravitational waves, ripples in space-time caused by cataclysmic events like black hole collisions. In 2015, the LIGO Observatory made history by detecting gravitational waves from two merging black holes 1.3 billion light-years away. This discovery opened a new way to listen to the universe, revealing black holes that emit no light at all. Since then, dozens of black hole mergers have been detected, including one involving a black hole 142 times the mass of the Sun, a so-called intermediate mass black hole, a missing link in our understanding of black hole formation. Perhaps the most iconic image of a black hole came in 2019, when the Event Horizon Telescope, EHT, unveiled the first ever picture of a black hole's shadow. Using a global network of radio telescopes, the EHT captured the supermassive black hole at the center of the galaxy M87, 55 million light-years away. The image showed a glowing ring of light around a dark void, the black hole's event horizon. It was a triumph of human ingenuity and collaboration, proving that even the most elusive objects in the universe can be brought into focus. Yet, observing black holes remains a monumental challenge. They are often hidden behind clouds of dust and gas, and their signals are faint compared to the vastness of space. New technologies, like the James Webb Space Telescope and future gravitational wave detectors, promise to reveal even more. But the biggest questions, what happens inside a black hole and what lies beyond the event horizon, still elude us. As we push the boundaries of observation, black holes continue to surprise us. They are not just cosmic curiosities, but windows into the fundamental nature of reality. Each discovery brings us closer to understanding these enigmatic objects and the universe itself. Crossing the event horizon of a black hole is a one-way journey into the unknown. Beyond this boundary, the gravitational pull is so intense that not even light can escape. But what happens inside? What lies at the heart of a black hole? The answer is both fascinating and deeply unsettling. At the center of every black hole lies the singularity, a point where all the black hole's mass is compressed into an infinitely dense, infinitely small space. Here, the laws of physics as we know them break down. Gravity becomes infinite, space-time curves endlessly, and the very fabric of reality unravels. According to Einstein's theory of general relativity, the singularity is the end of the line, a place where time and space cease to exist. But this raises a paradox. If the singularity is real, it would mean that our understanding of physics is incomplete. Quantum mechanics, which governs the behavior of particles at the smallest scales, doesn't allow for infinite densities. This clash between relativity and quantum mechanics has led scientists to propose alternative theories. One idea is that singularities don't exist at all. Instead, black holes might contain something called a quantum bridge, a tunnel through space-time that could connect two distant points, or even two universes. These hypothetical tunnels are known as wormholes, and while they remain speculative, they offer a tantalizing glimpse into the possibilities hidden within black holes. Another theory suggests that black holes might not destroy information, but store it. In the 1970s, Stephen Hawking discovered that black holes emit radiation, now called Hawking radiation, and slowly lose mass over time. But this raised a problem. If a black hole evaporates completely, what happens to all the information about the matter it swallowed? This is known as the black hole information paradox, and it remains one of the biggest unsolved problems in physics. Some scientists believe the information is encoded on the black hole's event horizon, like a hologram. Others think it might escape through Hawking radiation, scrambled but preserved. Then there's the idea of firewalls. According to this controversial theory, the event horizon might not be a smooth boundary, but a fiery wall of energy that would incinerate anything falling in. While this challenges our current understanding of black holes, it highlights how much we still have to learn. But perhaps the most mind-bending possibility is that black holes could be gateways to other universes. In 1963, mathematician Roy Kerr found a solution to Einstein's equations describing rotating black holes. These Kerr black holes don't have a singularity, but a ring-shaped structure. Some theorists suggest that passing through this ring could lead to another universe or a different point in space-time. While this remains speculative, it fuels the imagination and pushes the boundaries of science. Despite these theories, the true nature of a black hole's interior remains a mystery. The singularity, the information paradox, and the possibility of wormholes all point to a deeper truth. Black holes are not just objects in space, but laboratories for testing the limits of our knowledge. They challenge us to rethink the nature of reality itself. As we continue to explore these cosmic enigmas, one thing is clear. Black holes are not just destroyers of light and matter. They are creators of questions, pushing us to uncover the secrets of the universe, and perhaps even rewrite the laws of physics. Black holes are more than just cosmic curiosities. They are keys to unlocking the deepest mysteries of the universe. From their role in shaping galaxies to their potential to reveal new laws of physics, black holes are at the forefront of modern science. But what does the future hold for our understanding of these enigmatic objects? One of the most exciting frontiers is the quest to unify general relativity and quantum mechanics. These two pillars of modern physics describe the universe at vastly different scales, but they clash violently inside black holes. Solving this conflict could lead to a theory of everything, a single framework that explains all the forces of nature. Black holes, with their extreme gravity and quantum effects, are the perfect laboratories for testing such theories. Already, ideas like string theory and loop quantum gravity are offering new insights, suggesting that space-time might be made of tiny loops or vibrating strings. Another promising area is the study of supermassive black holes, which lurk at the centers of galaxies. These giants, millions or even billions of times the mass of the Sun, play a crucial role in galaxy formation and evolution. By studying them, astronomers hope to understand how galaxies like our Milky Way came to be. The Event Horizon Telescope, EHT, which captured the first image of a black hole in 2019, is now targeting other supermassive black holes, including Sagittarius A star at the heart of our galaxy. Each new image brings us closer to understanding these cosmic engines. Gravitational wave astronomy is also revolutionizing our view of black holes. Since the first detection in 2015, observatories like LIGO and Virgo have recorded dozens of black hole mergers, revealing a population of black holes we never knew existed. Future detectors, like the LISA space mission, will extend our reach even further, allowing us to listen to black holes merging across the universe. These observations could shed light on how black holes form, grow, and interact. But the future of black hole research isn't just about technology. It's also about imagination. What if black holes are gateways to other universes, as some theories suggest? What if they hold the key to time travel or the nature of consciousness? While these ideas may sound like science fiction, they push the boundaries of what we consider possible and inspire new ways of thinking about the cosmos. At the same time, black holes remind us of our place in the universe. They are both destroyers and creators, devouring stars and yet powering some of the brightest objects in the cosmos. They challenge us to confront the limits of our knowledge and to embrace the unknown. As we look to the future, one thing is clear. Black holes are not just objects in space. They are mirrors, reflecting our deepest questions about existence, reality, and the nature of the universe itself. The journey to understand them is far from over, and each discovery brings us closer to answering the ultimate question: what lies beyond the event horizon?